undeserved for now. So thank you. Pleasure to be here. So this is a version of a talk that I have given several times. For the first time, believe it or not, in 2017 or so, to the New York Skeptic Society. Right. So at the time, people were very skeptical about the whole thing, right? So which is hence the name. So I have updated it since. So there is a lot of slides. I'm going to try to go quickly. The agenda is quite simple. So I'm going to talk a little bit about what AI is to dispel some confusion, which I think is pervasive, frankly, in the world today, right? We are going to talk a little bit about the advances, at least the way I see them, right? A little bit about applications, right? So even though I work at Bloomberg, you know, I am not here to talk about Bloomberg or Bloomberg products or anything like that. If you have an interest in something like that, please talk to me afterwards. And then, of course, you cannot talk about AI today without talking about the topic du jour, which is large language models. So everyone at this point and their aged grandmother has talked to ChatGPT or something like it, right? So, and people see the promise, right? But there are also some challenges. And I'm going to talk a little bit about what these things are and how they work, and what they can and cannot do. Right, and then a little bit about trends and future directions. I don't have a crystal ball or anything like that, but you know there is a lot that we can easily forecast, right, just by extrapolation, right? And there are already signs of some of the things that are on the horizon. So AI is everywhere. You know, how do you know if you know there is kind of too much hype? Is when your taxi driver starts asking you if you should buy NVIDIA, right? That actually happened to me, right, 2-3 weeks ago. Right? I'm sorry? That is too late. So, and AI is indeed changing the financial industry at least, right? And in fact, the world at a very much accelerating pace, right? So there is a lot of noise about this topic. Right? And part of the reason for this talk, which I have given many times at this point, most recently in London and in DC on Friday to people in government organizations, basically is to dispel some of the hype and to make sure that people have a little bit more grounding in terms of what is actually going on. All right? So if you have questions, since the group is relatively small, feel free to throw up your hand. And let's go. So first of all, what are we talking about? All right, so AI is not new. Right? So in fact, the first real artificial intelligence programs that we would qualify as such today were developed in the late 1950s and early 1960s. Right? So this is when the first neural networks were developed. This is when perceptron was invented. Right? And in fact, one of the first real artificial intelligence programs, which was called the Logic Theorist, was developed in around 1958, 1962, which was intended, believe it or not, for science, right? So it was intended to prove theorems in mathematics. And for its time, it was wildly successful. It proved something like 24 out of 25 propositions in Principia Mathematica, right? So AI is a subfield of computer science, which is very broad. It covers not just machine learning, not just deep learning, not just language models. It covers everything that thinking things do. Planning, playing games, proving theorems, right? You know, all kinds of things, control problems, optimization problems, and so on and so forth. So within that large domain, right, there is a subset of methods that is called machine learning, which is where we apply statistical methods to these kinds of problems of cognition and reasoning. Right? So the distinction here is that larger AI involves problems which are solved essentially kind of top-down, right, if you will. Whereas machine learning methods, generally speaking, work bottom-up and you learn things from data. Right? Now, within machine learning, there is a smaller subfield, which is called deep learning. Right? This is where we build a particular type of a statistical model, which is a combination of many small elements, which are called quote-unquote neurons, in quotes, because they have very little to do with the actual neurons that you have up here. Right? They are mathematical abstractions of what is happening up here. right? And they're arranged in these deep hierarchies, right? Which is why these things are called deep neural nets, right? And then the large language models that so many people are so excited about are even a smaller subset of this stuff, which is a particular type of a neural network, which is called a transformer. So, this obviously has a fairly significant overlap with mathematical statistics, right? And the larger domain of data science, as people call it, is where we apply these methods to actually building products, right? How do you actually make this stuff practical? How do you apply it to the real world? So hopefully this at least gives people the right vocabulary to talk about, AI. Like, what are we even talking about? So, Bloomberg has been working in this space for quite a while. So first projects that we had undertaken using this technology date back to around 2008, 2009 timeframe, right? So this is before deep learning took over the world. This is before ChatGPT or transformers really, right? This is before anybody in the industry frankly knew what machine learning was or what you could do with it. So I'm going to talk very little about Bloomberg, but just to give you guys an idea of where we are and what we do with this stuff. So the first question that people ask is why, right? This was not an obvious step to take back then, right? The world was a very different place then, right? So the state of the open source community was very much nascent, right? So there was no PyTorch, there was no, TensorFlow, there was none of these things. So everything had to be built from scratch in-house. Right? It was very complicated. It was very expensive because these models are very data hungry. So where do you get the kind of data that you need? Right? That required human annotation in many, many cases. I personally annotated many tens of thousands of documents and other examples for machine learning models, right? Which is as tedious as it sounds, right? And the answer in many ways, right, is encoded in this picture. So this is fairly current. So this is up to about a month ago. This is the aggregate number of ticks that we ingest. Right? So ticks are basically trades, think of it. Right? So from every exchange in the world. And sometime about a month ago, we crossed the threshold of 650 billion ticks per day. Right? So that's 650 and then 9 zeros afterwards. Right? So just to give you an idea of what the dynamics here is, so like this little blip here, that's a 2008 financial crisis. All right? That's it. All right, so this chart is interesting in many ways, right? Because no matter how you cut it, no matter where, it will look exponential. All right? So this is what keeps our engineering management up at night. All right? This is why we keep building data centers. Right? And we have many. So, and this is just the structured data. This is just trades, right? This is the stuff where you understand everything about it, right? All the way back when I started in 2007, we were already ingesting something like 250,000 news stories per day. And today, that number is routinely over 2.5 million news stories per day, right? In 43 different languages, coming from about 125,000 different sources around the world. So my colleagues at Columbia who study journalism estimate that the overall aggregate number of news stories written in the world is about 3 to 3.5 million per day. So we ingest something like 3/4 of all news written anywhere. Right? So like we might not have a random newspaper on the corner in Malaysia, right? But we will have everything else, right? Everything that matters. And there is valuable information that is disclosed to the market using this kind of unstructured data, right? So to substantiate that, this is a case study that I have been using for a while, right? So this is an interesting one. In April of 2010, without naming names because they get upset if I do, this is one of the major US investment banks, right? They were sued by the SEC. The SEC is the Securities and Exchange Commission, right? So this is a major regulator in the United States who regulates the securities market, right? So, and they sued the bank for fraud, which is a big deal, right? And if you zoom this picture in, you will see something like this. Right? SEC back then did something rather unusual, right? In that they published the announcement of a lawsuit on their website and nowhere else, right? Which meant that no one saw it for 3 or 4 minutes, right? Until one of the Bloomberg journalists who had the unique bit of foresight to create a filter, kind of a search, right, which searched for a very specific set of keywords like lawsuit, SEC, something, something, saw the story, summarized it literally into one line, right, published that one line, right, as a kind of headline, right, breaking news headline, and that produced this sort of effect, right? So precipitous decline in the share price. So this is an interesting picture because you can read off a lot of information about how breaking news is priced into the market. Like if you're interested in how markets work, this is an interesting case study to look at, right? New York Times is in this picture, not because I particularly dislike New York Times, though I do have questions about their journalistic integrity, right? But because, you know, this is not the kind of thing that moves prices, right? So most news that people see, most things that you read are commodity news. You know, New York Times, AP, etc. These are not the kind of news that actually move prices in this way, right? So for that, you need subscription news, right? This is where the company issued the rebuttal, right? Nobody believed them, obviously, right? So, so the share price never recovered. So it's an interesting case study in terms of how the actual market works in kind of presence of this sort of sudden shock, right? And this is not a unique occurrence in any way. I have literally tens of thousands of pictures like this. Yes?
What is your opinion of zero hedge?
Complicated.
Okay.
Right. So, you know, this happens all the time, it turns out. This happens hundreds of times per day, right? In a variety of fairly complicated circumstances. So, for example, things like, you know, merger and acquisitions announcements, right? Or outcomes of clinical trials, right? Or, you know, for example, this was an approval of a drug by FDA for a rare drug, for a rare disease or something like that, right? Or complicated things like this was a breakdown in negotiations in an M&A deal or some sort, right? So there is no simple set of rules you can write down that captures all of this stuff, right? So, which means that the only technology that we had found realistically that allows us to actually extract value from this kind of data, right? Especially given the volume, the variety, right? And the speed at which we have to deal with it, right? At peak volume, we get something like 1,200 stories per second, right? So there is no human being who can consume even a small fraction of this information. So how do you make this useful? How do you make this kind of thing actionable, right? And that led us to build tools for people to take advantage of this information in various ways, right? So I will talk a little bit about what those tools look like in a bit, right? So there is a lot going on, right? You know, I run a conference with Columbia University, which is called Machine Learning in Finance. This year is going to be 11th year. It's September 25th. Please come if you're interested. It's a very technical conference, though, so like it's actual academic papers presented. And the first time I put it on was in 2014. Right? And at that point, it took me 3 months to find enough people willing to talk about what they were doing. Right? There was just not a lot of people 10 years ago talking, like, willing to talk or even doing anything with machine learning in finance. Right? Conversely, last year when I was preparing the program of the conference, I had to read 1,300 abstracts of papers. And before you ask, you couldn't use AI for it at that time. Right? So I actually had to read for a week. And there are literally thousands of papers, academic papers, right, that are published per year in a field which is as narrow as just machine learning in finance, right? So one of the major conferences in AI is called Neuro Information Processing Systems, or NeurIPS, right? So last year it was 16,000 people. Right? Just gives you an idea of how much effort, how much attention is being put into this field, right? There has been a lot of progress in open source or open weight models. So people may have heard of things like Llama and DeepSeek, right? And Falcon and so on and so forth, Mixtral. A lot of work is going into things like new architectures and new training methodologies. So, you know, different kinds of variants of transformer architecture, linearized attention to make these models less expensive to run. Hybrid models like alpha geometry, which I will talk about in a bit, right? Truly novel architectures for things other than text, like pixels, right? Agentic AI, DeepSeek kind of models. distillation, etc., etc., etc. So there is quite a lot going on. And all of this leads to novel applications. So in finance, pretty much every part of the financial workflow, starting from security selection and asset allocation all the way down to execution, every part of it has been automated using machine learning somewhere by someone. Like throw a dart at it, you will hit something that someone had done with AI at this point, right? Which is new, by the way. So like I said, 10 years ago, this was not a thing. So this happened very recently in the last, call it 5 years or so, right? So things like hedging and pricing derivatives and then pricing other things like fixed income instruments, execution, strategy development, all kinds of things had been done with AI in finance. Outside of AI, this stuff is being used for design of novel materials and drug discovery, healthcare, including personalized medicine, right? Things like robotics, education, law, God help us, right? The enlightened state of Pennsylvania uses AI to decide sentencing for criminals. Right? Happy thought, right? You would better hope that model is right? And that is part of where a lot of the research attention is going into. So there are, in fact, new conceptual directions which are still being introduced. Right, so this is a very rapidly evolving field. So for example, for people who are more technical in the audience, right, there is this new idea which is called machine learning with physical priors, right? And this warms my heart as a physicist because I was a physicist in a previous life, right? So like all the things that I used to know about differential equations are suddenly relevant again, right? Because this is a way to integrate differential equations with neural networks, right? So like you write down the causal structure of your data generating process by hand as an equation, and then you learn the missing bits from data as neural networks. So which is a lot more principled way of going about learning complicated dynamics than just let's throw a giant neural net at it and see what happens, right? As these models are applied to mission critical applications like law, for example, or medicine, right, more and more attention is being paid to things like algorithmic fairness, differential privacy, causal structured prediction, and this all overall falls under the umbrella of AI safety or AI guardrails, right? So this didn't used to be a thing, right? So like I remember talking to people about explainable models 10 or 15 years ago, and people were looking at me as if I was an alien. Like, why would we need that, right? And now when this thing is in self-driving cars, suddenly everybody cares, right? So explainable AI is a big thing. Adversarial robustness questions, which were largely theoretical until 2 or 3 years ago, are suddenly practical, right? Because now everyone has one of these AI models in front of them and can talk to them, right? And we would like to make them safe to use, right? Like we don't want the thing to tell you how to cook meth in your kitchen, right? And or how to build a bomb or whatever, right? So this is one way to quantify the progress. So this was done by a researcher whose name is Maxime Labon. He did a lot of work. So green ones are the open source models, and the red ones are proprietary ones, right? So including things like ChatGPT or whatever. You can ask a lot of questions about what is happening here, like what the hell happened here, right? So like the performance of these models, especially proprietary ones, right, varies greatly depending on when you measure it. Like you evaluate the model on a simple problem like whether this is a prime number or not in April, and it is 99.8% accurate, and then you evaluate it on the same problem using the same data in July and it's 0% accurate, right? So what happened? Nobody knows, right? The trend was pretty obvious even back then, right? So suffice to say that it's not enough to evaluate just models, right? You need to evaluate the overall system end to end, right, for the particular application. But more recently, the trends have really converged, right? And for the first time, pretty much the open source models like Llama have essentially converged in performance with proprietary ones. Right, DeepSeek is part of the same trend more recently, right? And in fact, if you look at the leaderboard on any given day, depending on the problem that you are looking at, they will just permute on a weekly basis, right? As things are, kind of changing. So some interesting things to note here, right? So people who have used ChatGPT will remember this model, GPT 3.5 Turbo. Yes? Some people? All right, so this one was already pretty capable. People will agree, right? This was also enormous. So this is like 175 billion parameters. It took tens of millions of dollars to train, right? Conversely, this is something that you can run on your laptop, and it is equal or better, right? And this happened within a year, right? So there is clearly still a lot to learn, right, about how to build these models in an optimal way, right, in terms of what the right scaling laws are, how much data do you need, how exactly do we train them, and so on. So let's just say that it might be premature to settle on one model to rule them all, right? So because things are changing so quickly. All right, same thing here. So this one is something like 1.7 trillion parameters, which boggles the mind, right? Because that's starting to approach the number of synapses in your brain, right? This one is 4 times smaller, right? And it is on par or so, right? So,
Question.
yes.
Is one of those the one that was in the news, the Chinese one that's sort of simpler or more efficient? Is that?
No, DeepSeek is not in here because this is up to about a year ago.
Okay.
Right, but at this point, if you were to continue this trend, so it's basically kind of going like this, right? And DeepSeek is somewhere in that same band, right? So it's not massively better, but it's not massively worse, right? It's just cheaper and kind of more efficient in many ways. So now, what can you do with it? Well, we, like I said, started a long time ago, right? And the first problems that we applied this stuff to were problems of search and discoverability and alerting. So basically filtering data like news stories, for example, right, to create actionable alerts exactly of the type that I alluded to when I was looking at that case study, right? Like, wouldn't it be nice if you had a machine that could detect those stories, right? Like that SEC announcement when it happens, right? Because you can trade a lot of stock in 3 minutes, right? So we started with things like entity tagging and, then topic classification, like is this story about Google, Apple, or Microsoft? Is it about China or Russia? Is it about oil or gas, terrorism or war or whatever? So and at this point, we have literally tens of thousands of these models running in parallel, which basically attach these kinds of concepts to text, right? Again, in many languages, right? So, and people use this for what you might expect, right? So either event arbitrage or monitoring, right? Or for algorithmic trading directly, right? Risk analysis and so on. And then over time, we added other things. So machine translation we played with, novelty detection, right? Event recognition and kind of extraction. And then today, the domain of application looks something like this. So this is basically all of natural language understanding known to man. Like you literally open an NLP textbook on any page, we do something like it somewhere. Right? And there is also a lot of things that don't fit into text at all, right? So which is something that I'm going to talk about later, right? So time series analysis, anomaly detection, recommendation systems, search, right? We use this everywhere. The AI engineering group, which I started in 2008, at this point there's almost 400 people, right? So, and that's just the people who are dedicated to model development and research. Right? The larger community of people within our organization that actually uses these models to build things is around 4,500 people. So basically half of our engineering, right? So this is used for everything, right? So this has been very successful in solving all kinds of different problems for our clients, right? And there is a lot more where that came from. So that's enough about Bloomberg, right? Because you're not Bloomberg customers. Right, and now, of course, the thing that everybody is interested in is large language models, things like ChatGPT or something along those lines. So first is, what are these things? Well, fundamentally, a language model is actually quite a simple thing, right? So it's just a way to describe a probability distribution over strings. Right? So you give it a string of text, and it will give you a number which says how likely that string of text is given the language that it came from. Right? there is a variant of this which is called autoregressive language models, which work like ChatGPT, where you give it a prefix, right, and then you can ask it for the probability of subsequent word, right, and it gives you a probability distribution of what the subsequent word might be, right, and then the way you use it is you sample the ones with highest probability, right, and then you repeat, right, and it will keep generating text like this, right, so sounds very, very simple, right? So now the question is, how do you build this probability distribution? How do you actually encode this information, right? And that is where the interesting part starts, right? Because these models are trained in 3 steps, roughly speaking, right? So again, taking a step back, this is a giant neural network, right, of a particular type, which is called a transformer, right? And it's basically a string-to-string transducer, right? Like you give it a string, you get back a string. Fundamentally, that's what it is, right? Now, the way that these models are trained is the following. So there is a first step, which is called pre-training, right? And this is done using something called the missing word objective. So this simple idea is the idea behind pretty much all the innovation in natural language processing over the past 10 years, right? So you collect all the text you can get, literally the entirety of the internet. You break it up into phrases and sentences, and then you corrupt that text by removing some words. And during training, you ask the model to guess the missing word, right? So this is the expensive part, because you have to go over trillions of tokens of text, right, potentially multiple times, right? So this is a part that costs millions of dollars, right? Then this is not enough, right? Because if you try to talk to a model which is trained this way, and you give it a sentence like, you know, Berlin is the capital of Germany, then what it will do is will keep generating more of the same. It will go, Paris is the capital of France, you know, London is the capital of the United Kingdom, and it will keep going like that until you tell it to stop, right? So to make it useful, you need to make it conversational somehow. And that is done using a separate step, subsequent step, which is called instruction tuning, which is a variant of supervised fine-tuning, for which you need a different kind of data set, right? It's a data set of question-answer pairs, right? Which is manually created. It's very expensive, right? So this data set is usually much smaller, right? So, and this is the part that makes this model into a chatbot. And now if you tell it, Berlin is the capital of Germany, it will go, yes, Berlin is a beautiful city. Would you like to know more, right? Yes?
You said that the question answers is manually generated. Now with the chat, what else do they generate question answers in? What models?
Yeah, so I will get to that in a bit, right? Because nowadays we generate a lot of synthetic data, right? So you can ask these models to generate more of the same if you give it examples, right? But there are caveats and limits to what you can do with that, right? So now you have a chatbot, right? That is not enough either, right? Because again, there are certain questions that you don't want to answer, right? Like in finance domain, if I ask a model whether I should buy Apple or not, we might have a difference of opinion about what kind of answer you should get, right? But if somebody asks, should I leave my wife, you definitely don't want to answer, right? So, you know, similarly with other kind of things like having to do with explosives and weapons and so on. So there is a third step, which is called safety training, which is done yet another way using a third data set, which is essentially kind of a set of questions with yes or no answers, like should you answer this or not, right? And then there are also subsequent details in terms of post-training conditioning, because you can give these models instructions before you talk to them. So, but fundamentally, most of the intelligence, quote unquote, right? Most of the knowledge that this model accumulates is using that first step, using the pre-training step. And if the underlying logic of what it is learning is so simple, why are they so powerful? That's $1 billion question, right? And that answering that question requires thinking from first principles, right? So what can you learn from the masking objective? So here are some examples. Let's assume we play this as a game, right? So I give you a sentence and I ask you to guess the missing word.
You're gonna guess all.
Right. These are not designed to be difficult, right? So, well, it turns out to play this game well, you need to know quite a lot about the world, right? Like you need to know about locality of things, you need to know names of things, you need to know things like classification, like whatever goes here probably swims in water, right? You need to know a lot of linguistics to understand prepositional attachment and other complex linguistic phenomena, right? You might need to learn sentiment analysis, like the movie clearly was not great, right? In fact, depending on what word or token you emit in this sentence, you might actually have to do arithmetic to answer, right? So, and it turns out that in the general case, playing this game well requires general intelligence, right? So like this is why these models are so powerful, right? Because they memorize everything they see during training, right? And thereby they learn a lot of complicated semantics, like they learn a lot of things about the world, right? And then when you make it conversational, right, it will regurgitate whatever it had seen during training, right? Potentially in novel combinations, right? But obviously there are limits to how these things work, right? So like given the logic of how they are trained, given what this thing is doing, right, these models are different, right, in substantial ways from the previous generations of AI, right, in that they are very general, right? By virtue of this training process, they are able to handle many tasks, many of them out of the box with no subsequent training or tuning or anything like that, right? So they are very broad, right? So they, like I said, memorize everything, right? And they're uniquely accessible, right? Because you talk to it in English or whatever instead of code, so you no longer need to be a software engineer. Which means that your kid can talk to it, or your aged grandmother, like whether it's a good thing, I don't know. And the reason I don't know is because the most recent surveys indicate that something like 3/4 of all school teachers in the United States are using ChatGPT to create lesson material. I leave it as an exercise to the audience to estimate how many of your children are using ChatGPT to solve those problems, which leads me to question where is the learning happening, right? Right? So they are effective at many tasks, everything that has to do with language, summarization, question answering, synthesis, style transfer, whatever you can think of. But also importantly, and this is underappreciated still, they're also very good at code generation, which is not just a thing for software engineers, right? This means that you can use one of these models essentially as a universal language interface. You can use it to talk to other things, like a drone or robotic arm or a bond calculator or whatever it is, right? So you give it instructions in one language and you ask it to translate that into another language, even if that's a machine language, it will do it very well, right? And people have already done a lot of interesting stuff with this, right? So now these models do show a great deal of promise, right? So GPT-4, Claude, Gemini, the most recent one is very, very promising. Right? But you can ask, right, a reasonable question, like can these models reason the way that we reason? Can they plan the way that we plan, right? And so far, the answer is definitively no. And you can show this empirically, actually.
Okay.
Yes.
Question. So I understand that, let's say, if my vacuum cleaner is broken and I ask ChatGPT, what could be wrong? It has seen a lot of text about vacuum cleaners and the way they get broken.
Yes.
And the answer is the most probable
Most
sequence
likely,
of characters.
yep.
Okay. But if, let's say, there is a book I would like to get summarized, that book might not have been seen.
Mm-hmm.
It's a new document, let's say, some legal document. How is that summary going to be meaningful?
Right, so you essentially give that document to the model as a prompt, right? So and that augments its state at runtime, basically, right? And then you ask it questions, it will base its answers on the input that you gave it. That input could be quite long, right? At this point, it could be 100,000 words or something like that, right? Does that answer your question?
Kind of. So it's so the weights in the model are still the same, right? Based on what it has said before.
With a small caveat, because what is actually happening at runtime is that it turns out it simulates like 1-2 steps of stochastic gradient descent. So at runtime, it simulates weight updates, right? But those are ephemeral; they're temporary, right? So like this is an example, right, from a paper by one Subarao Kambampati, right? So he is a senior academic at the University of Arizona. He is a key person in the computational planning community, so like old school AI, right? And this is a test of all of these current models on a problem which is very simple for human beings, right? So it's called blocks world, right? So you have covered blocks on top of each other, right? And the solution is you're given instructions and you're supposed to say, what sequence of steps do you need to take to get to the end state? Like you want 3 blocks stacked on top of each other. Which blocks do you need to move in what order? Like a child can solve this, right? You give these problems to these very powerful language models, and even given many attempts, they don't do very well. Still, today, this is from a month ago, right? Furthermore, it turns out that there is another interesting detail to this. So suppose we take those problems, right, and we obfuscate them, like we mask the names of colors and we replace them with random strings, right? So the structure of the problem did not change. The solution to the problem did not change, right? But now the model had never seen it during training or otherwise, right? And suddenly the performance of these models goes through the floor. Now they can handle none of them, 0. Right? Which means that a lot of the performance of these models is just memorization. It's not doing reasoning, it's guessing, right? It's guessing extraordinarily well, right? Because again, it's like an idiot savant that read the internet. Like it knows everything, right? But doesn't understand anything, right? So it will tell you whatever you want to know, right? Given the way that these things are trained, if you ask it why the moon is made out of cheese, it will tell you a very plausible story for why the moon is made out of cheese, right? Even the reasoning models, so to say, right? The reasoning in quotes, because again, they are not really reasoning, right? So, because what they are doing when they say these models are doing quote unquote reasoning is essentially they're doing search, right? So like they're generating many candidate paths in terms of solution, and then they basically pick the most plausible one, right? So, and the reasoning part is very, very expensive. So like I'm talking like multiple orders of magnitude more expensive, because you have to run this thing many, many times, right? To generate this tree of reasoning steps, right? So still a lot to learn, right? So one problem that, now the things are moving very quickly. So for example, a year and a half ago when I originally wrote this slide, GPT-4 would struggle with 3-digit multiplication. At this point, they have basically saturated high school math, as in like you give them any kind of high school problem in mathematics, it will solve it. Right, just again, based on memorization, yes?
Wolfram Alpha was solving algebra about
20 years ago.
20 years ago, yeah.
Right.
Okay.
But that's a very, very different kind of model.
Oh, okay.
Right?
Purely mathematical.
I will talk a little bit about this in a moment, right? Yes.
Why is this? Recently I asked ChatGPT to more like to calculate the Reynolds numbers for a specific problem.
To calculate what?
Reynolds number. You know Reynolds.
Reynolds.
I got 3 solutions, 3 different solutions. That was like 3 weeks ago.
Yeah.
Why? I mean, it's simple. It's super simple. Why is that impossible?
It's not impossible, right? So it is highly sensitive to the way that you ask the question.
I asked exactly the same.
Right. And they are not deterministic, right? Again, they are sampling a probability distribution, right? So another question that I was interested in, for example, is do these models see the way that we do, right? So like some of these models now understand not just text, but images, right? So it can not just generating images, but you can give it an image and ask it questions about it, right? Well, it turns out they don't, right? And the way you test this is actually quite subtle. So there are these images which are called optical illusions, like visual ambiguities, right? There's something like you look at it one way, you see a vase, right? You look at it another way, you see 2 faces, that sort of thing. Again, trivial mostly for human beings, right? And you give these kinds of images to ChatGPT or another model, right? And the standard ones, the ones that are well known, it will understand, quote unquote, right? Now, if you generate novel optical illusions that no one had ever seen, and there is a tricky question about how to do that, but we came up with a way of doing this. right? You give it novel optical illusions and it doesn't understand them at all, right? Again, memorization, right? Even in visual space, right? So it memorizes everything it sees too, right? So if you want to solve hard problems like that, right? If you want to solve problems involving proof, guarantees, right? Hard constraints, right? You end up building things which are a lot more complicated, right? Which is the world where I live, right? So like for us, for our domain, right? You know, guessing is not okay, right? You need to ground these models in real data, right? In things which are deterministically known, right? And while I cannot talk in detail about our approach, except for public research that we actually submit to conferences, last year I got a bit of very useful help. DeepMind published a paper which was called Alpha Geometry. If you haven't seen it, I highly recommend it, right? So they tried to solve Olympiad-style geometry problems using one of these models. Anyone here participated in IMO? Right, International Mathematical Olympiad, right? So I participated when I was a kid. I got to state level, right? Like if you solve more than 20 of these problems, you are guaranteed to be a world-class mathematician. These are very, very hard, right? You give them to ChatGPT and it solves none of them. It doesn't understand them at all, right? Because it's not grounded in the real world in any way. It hasn't seen geometry problems, right? Not in sufficient quantity to be able to memorize things like that, right? So instead, what these guys had built was a very interesting neurosymbolic hybrid model. And this is the way that model works, right? They trained a language model of ChatGPT variety using a whole lot of synthetic data, to your point, about geometry, which we automatically created, right? And then they basically prompted that model to generate a suggested construction in geometry given the problem statement. So you give it a problem and you ask it for the most likely next step. And it generates a guess, right? So like draw a circle here with this radius, right? You take that combined statement, right? And you plug that into a deterministic theorem prover, like lean or COQ or something like that, right? Which proceeds completely deterministically the way that a human mathematician would, from axioms to consequences using kind of standard logical rules, right? If it succeeds in proving your proposition, great, right? If you didn't succeed, you go back, you try again, and you keep going like this in a loop, right? So if you think about it, that's again a kind of search, right? It's just that it's search in this very complicated space of theorems, right? And remarkably enough, they doubled the previous state of the art and nearly matched the gold medal Olympiad level, right? Which is a remarkable achievement. I have to give it to them, right? But there are also some observations we can make, right? And the observations, this is directly from the paper. This is not me saying it. This is Google researchers saying this, right? For which I'm very grateful, because nobody was listening to me for some reason. Right, so they say that these kinds of search methods have no theoretical guarantees. It might work or it might not. Right? They also say, by the way, by today's standards, that model that they built is not large, right? It's like 10, 20, 100 times smaller than ChatGPT, right? So you don't need a giant model if you're clever, if you have the right data, and if you know what you're doing. Okay? And then they say that the framework that they developed requires the following ingredients. It requires a kind of a implementation of a model of the domains, definitions and objects, right? So like in geometry, these would be points, circles, lines, whatever, right? In our world, these might be securities, prices, right? Portfolios, whatever, right? You need a way to randomly sample those things, right? And you need a symbolic engine that can operate on them, like a theorem prover or something like that, right? And that symbolic engine cannot be a black box. It has to be traceable. It has to be understandable to a human being, right? And if you can do that, you can do remarkable things, right? You can build a system which will give you hard guarantees, right? Which will actually give you a human understandable proof and will discover novel proofs. It has already done that, as in like this system generated novel proofs for theorems that we did not know, right? But again, it's search. And then they say in an understatement of the century that, you know, there are non-trivial technical challenges in implementing every part of this recipe, and it requires deep domain expertise. Right. Yes, indeed. Right. So this is still far from anything I would call robust or trustworthy. Yeah. Yes, please.
Gary, when I think about like when, image generation started, it seemed very inventive. Like it created things that wasn't memorizing anything. It was like making something look amazing that had elements.
But how do you know? But how do you know?
Like the avocado chair, or like a lot of architects got interested in. Like,
Yeah.
And created really beautiful like synthesis of
Yes.
different domains.
Right, so that's a different kind of model, right? These are called the diffusion models, right? And they're trained in a different way. And again, you don't know what went into that model during training. What had it seen, right? So it's very difficult to diagnose like what part of the output is original versus what part is, just a clever juxtaposition, right, of things that it had actually seen before, right?
I kind of wonder why, like when you play with all these things, they seem so novel to the users.
Right.
These are people who like are, versed in architecture or whatever. But then somehow when you do language or these transformers, you don't get that novelty.
You do.
You get that sublime.
Again, it's very sensitive to the way that you ask questions, right? But a lot of these effects, right, are actually humans in the loop knowing the answer, right, or kind of having the aesthetic judgment to say that, oh, this is beautiful, right? So what are the limitations of some of these models, right? Because there are clearly many, right? So we talked about the reasoning and planning, right? So even though the situation is rapidly changing, this is still quite an issue. Computational complexity for these models is very high, right? So like as I shown, right? So they have basically limited amount of data that you can give them at one time, right? Because it scales quadratically with the length of input. Everyone at this point has heard and probably encountered hallucinations. Yes? These models make things up, right? And that is universally misunderstood, right? That's a feature, not a bug. Because when you're asking a model like that to generate code for a problem that it had never seen before, you're asking it to hallucinate. And you can't have one but not the other, right? And the reason this happens is because, again, by virtue of the method that I described for training, there is no notion of epistemic uncertainty anywhere in the training process, not in the data, not in the training algorithm, not in the objective function. There is nowhere to extract second-order information about confidence values or anything like it. So this issue is not going away, no matter what Sam Altman tells you, right? Until we develop a different way to train these models, which we do have, by the way. There are ways of training these models in a different way, but they don't scale to the sizes of data that we currently use to build them. All right? Yes?
Does that relate to the fact that these models have, let's say, no intuition or gut check? Like sometimes, whether it's a text-based question or whether it's something that I might use like generative visual, a lot of the times it's decent, but when it's wrong, it makes absolutely no sense. Like a fifth grader would know that like the GDP of China is not 1 cent, but sometimes it will come up with these ridiculous things like
Yes.
that.
Yeah, so again, it's basically it memorized whatever it had seen during training, right? Like, and you can easily take it into regions of that training space, like where there is like here be dragons, like there is nonsense, right? Or just not enough ground to stand on, right? So like it will just generate random stuff. Right? The farther you are away from a training data distribution, the worse the output is going to look like. Yes?
You anticipate they'll have probabilities assigned to answers where it tells you this I'm very confident about, this I'm just making it up?
Yeah, so in fact that is already happening to a certain extent. Like the output of this model goes through something called the softmax layer, so there is a natural probability assigned to it, but that's not the kind of probability you're looking for. That's a probability of a token, not the probability of correctness, right? So, and the probability of correctness requires something altogether different, right? So like that's a lot harder, right? So cost of training these models is enormous, right? So you're talking about millions of dollars, even for the smaller one, which means that they're largely static. That means you cannot retrain them at will, right? Which means that, to your point, right, like if you want the thing to, answer questions about a particular document, you have to give it the document as a context, right? So, which is described using fancy words like retrieval augmented generation, right? Well, I have an anecdote about this. Cyril will back me up here because he used to work for me. We started working on the natural language interface to the Bloomberg terminal in 2014, right? So you had been able to ask natural language questions to the Bloomberg terminal since 10 years ago, right? And the way that system worked, right, is as follows. A user would type in a question. There is a model, not a transformer model, but a different kind of language model that would take in that string, right, and then convert it into a sort of a structured representation, right? So like somebody types in Chinese companies that had dividend yield over 5% last year, right, and that turns into country equals China and whatever asset class equals question mark, because it could be bonds, it could be equities, it could be something else, right? So concept equals dividend yield, number equals 5, units percent, relation less than, that sort of thing, right? And today we also, in addition to this, generate an embedding, which is a kind of a vector numerical representation of the answer, which you can then use for unstructured retrieval, for just find documents that look similar. But this structured representation you can actually use to turn it into database queries and to API calls, into calls to other systems, right? And this is something that had been around for a while. You collect the answers, you can rank them, which is what you used to do, or nowadays you can take the candidate answers, paste it into a different language model, which will then generate text around them to generate an actual flowing answer. And we wrote a paper about this in 2016. Right? And we submitted this to a computational linguistics conference called ACL, Association of Computational Linguistics. And the paper was rejected. And the reviewers flat out just did not believe us. They said, this will never work. This cannot work. Right? And then I went to the conference and showed it to the people and said, here it is. What do you mean it doesn't work? Right? And then people started talking about this retrieval augmented generation stuff. And I went is that what it's called? Because we have been doing this for 10 years now. We just didn't know what the name was. So this is actually quite tricky to get right, especially if you want the results to be reliable, trustworthy, and transparent. Yes?
So what you're basically saying is that there is no reasoning. This is a recursive system, and they're just retrieving from large data sets, and they're doing so after learning the probabilistic.
So this is kind of a hybrid model, exactly of the same type as I described with alpha geometry, right? So independently, people have converged to roughly the same solution, right? So, and this gives you kind of the best of both worlds in the sense that you are relying on the power of the language model to understand the input, right? But then the retrieval is fully deterministic. You're not relying on the model to memorize things, right, or to synthesize answers or anything like that. So it's grounded in real-world data, right? Which gives you transparency, reliability, and so on. Yes?
Very, very basic question, but the LLMs are absorbing facts, but you can have contradictory facts.
Yes.
How does it handle that? Or
It
opinions?
doesn't. It doesn't.
Yeah.
Right? Whatever it had seen during training is all equally probable, right? So it will remember both things, right? And depending on what question you ask, you might end up with either one. Yes?
So some people think that what makes humans unique is not the opposable thumb, but the ability to imagine. And when you're imagining, you're creating a whole series, as much as your brain can conceive of options, they don't need to be in the real world. You construct them in your mind, and then you sift through them. Mm-hmm. And that's based on the amount of data, life experience, and so on and so forth, which then gives you what you call intuition, but it's subconscious data processing. when you said hallucination is a feature, not a bug, could you argue that unlike where people say these models are hallucinating and humans don't do that, could you argue the exact opposite?
Oh, humans do this.
Could you say that humans are, that imagination is intentional hallucination, and therefore what we are saying is a unproductive area and something that needs to be squelched is something that we should go all in on and try to almost exacerbate as a problem, and
Right.
would we then be able to get, because of the sheer amount of processing power, the ability to then, in a roundabout way, arrive back at intuition?
Right, so there is a critical difference, though, between the way that these models learn and the way that humans or other thinking things learn, right? Because we learn not just from text, right? We learn from multimodal input, right? And we learn, in a very different way, which is a lot more efficient, right? By the way, imagination is not a feature unique to humans, right? This has also been demonstrated in other mammals, it has been demonstrated in dolphins, it has been demonstrated in birds, it has been demonstrated in spiders, believe it or not. There is this thing called Portia spider, which is a fascinating animal, right? Like if you look it up, you will understand what I mean, right? Because it clearly can visualize things, right? Observe prey and then plan a path where it cannot observe the prey anymore for most of the path until it gets to where it needs to be to attack. So it definitely has an internal state which is rich enough to represent goals, right? And to represent complicated 3D things like, path from point A to point B crawling over things, right?
But that may make the point even more that in an evolutionarily adaptive way to arrive at solutions, in many species, just the how
Yeah,
to
that's a
process
very useful
data
feature.
is that feature.
It's a very useful feature, don't get me wrong. And yes, humans and other things do this as well, right? But we are grounded in the real world in a way that these models currently are not. That's the important bit. Yes?
You mentioned the transformer model, which I think they also call multi-headed attention.
Yes.
Can you give us some intuition why that was so powerful?
Sure. So this is a little bit technical, right? So these models are neural networks which are sequence models, right? So like they look at sequential input like text, right? And they're then able to make predictions about the output, right? Like about something about that text. So in this case, it's making predictions about the probability of subsequent tokens. It could be predicting other things as well. So we had networks that had been able to do this for many years, right? So like they are called recurrent neural networks, right? So there are many, many architectural variants of this, right? The problem has been that those previous generations of RNNs, they don't scale particularly well because they essentially don't have memory, right? So, or the amount of memory that they have is quite limited. So essentially every part of the input that they observe is equally likely, right? And therefore, essentially, like at some point you saturate the memory, right? Like, and you start losing context which had occurred a long time ago, right? Or far enough in the sequence, right? So the innovation of a transformer architecture is basically this attention mechanism, which is essentially a way to selectively pay, quote unquote, attention, right, to different parts of the sequence in a problem-dependent, input-dependent way, right? So, and this gives you much more efficient neural network architecture in terms of A, training, and B, ability to handle long input.
So it's a memory enrichment focus. So rather than trying to learn the whole long
Yes.
thing, maybe the beginning of the last clause was
Yes.
going to be the important
Correct.
thing.
So there is a website which is very useful, which if you want to, you can look at, which is called the Illustrated Transformer by J. Alamar. It has beautiful visual illustrations for how this actually works. And it's not particularly technical if you don't want it to be. So look at it, you will immediately see what I mean. Right? So anyway, cost of inference of these models is also enormous. So one example is one of our major customers, a sovereign wealth fund, again, without naming names, had partnered with OpenAI to build their own version of GPT-4, which is a very expensive proposition, right? And this is one of the few organizations in the world that have both the data, the money, and the wherewithal to actually do such a thing. And they did it, and they were successful, and they were very pleased with themselves until they realized they were spending somewhere between $30,000 and $50,000 per month on inference, right? Because people were using the thing to parse PDF documents. Like guys, if this is the best use you have for one of these models, I have things to tell you, because they can parse PDF documents a lot cheaper, right? So, all of this progress leads people to, make predictions which in retrospect look mildly insane, right? So again, this is not new. So as a excurse into history, right? I thought it might be worthwhile to look at what people were saying back then, right? So like when we did originally, right? Started working on this stuff, people who in retrospect really should have known better. So Minsky, when he said this, was the head of a computer science and AI lab at MIT, right? In the 70s, people were of the opinion that we might have human-level intelligence within a year or two, right? Which obviously did not happen, right? Because a lot of these problems are very, very hard, right? And we're only now realizing how hard some of them are, right? And then now we're also making a lot of progress, right? And then people, well, this obviously didn't happen already, right? So are again saying things which probably are going to look mildly insane, right? It's very difficult to predict the future, right? And there's a quote by a Greek philosopher whose name was Diodorus of Sicily. And what is strange is not that the unexpected things happen, but that not everything which happens is unexpected, right? So, which is, I think, a beautiful way of putting it. My own timelines for superhuman intelligence are considerably longer than this, right? So, and these are some of the surveys, right, of experts that had been done. So starting with 2009, right? So this was one of the first conferences on artificial general intelligence, right? So majority of people were thinking it would never happen back then, right? And then, again, you're talking about 2200 or something like that here, right? Being the majority view. And then things changed roughly around 2013, because at that point, deep neural networks won the ImageNet competition. Suddenly, right, people saw the potential. So this is my own kind of integration of many of these surveys, plus my own survey of researchers, people that I actually know and trust, right? So again, in 2017, again, majority of people, it would happen, 100 years from now or never. Right? But in the past 10 years, these estimates have been kind of moving closer and closer. Right? Now, the thing is that you don't need strong AI to generate massive disruption and impact on the world, right? So, I wrote this slide originally in 2016, right? And people laughed at me. They're not laughing anymore, right? Because you can affect vast societal change even with weak AI, right? So as we already see. So some estimates, there are estimates that kind of say that somewhere between 10 and 50% of all employment is at risk of automation in the next 25 years, right? Something to think about. And I was part of this non-governmental organization, which was called the Shift Commission for Future of Work in 2016, 2017, where we actually studied this question. And we would show pictures of self-driving cars to truck drivers in Virginia. And these people would look at these videos and go, that's really cool. Like, here is a machine that is literally going to take your job, right? And these people don't have the cognitive vocabulary to understand what is happening, right? So the best scenario that I anticipated was profound uncertainty and upheaval, which is exactly what we're seeing realized. Right? So, the overall trends obviously are larger, faster, better. Look at all the content across all languages. We can build neural models for pretty much everything at this point. right? Multimodal kind of models, agentic AI, co-pilot style assistants, hybrid models, for in finance, a lot of this stuff is now being applied to deep reinforcement learning to trade actual autonomous trading agents, right? But finance is far away from most people's daily lives, right? Like you're not going to be building autonomous trading agents, right? Probably, right? Unless I don't know something about, right? So, what could you do with it, right, for the real world, so to say, right? Well, you can do a lot of things with it, and there are, in fact, early signs of many of these things, right? So you could imagine applying these models in climate adaptation, right, to build, early warning systems or monitor biodiversity. This is already being done today, right? Predictive maintenance using sensor data, as in like you have a drone with a camera that goes over a bridge, right, finds cracks, right, and then you do maintenance when and where it's needed, right? Autonomous equipment, right? Supply chain management, right? Not just to forecast demand, but to create novel molecules for preservatives, so for legal, right? So like I don't need a lawyer anymore, literally. Like I was being offered a private equity deal. I gave the documents to ChatGPT. It did a better job than my legal counsel. I kid you not, right? So language reconstruction for preservation, right? You could imagine interactive AI collaborators for artists. That is already happening today, right? So for musicians and visual artists. In health, personalized medicine, right? Early detection of mental health decline. In science, this stuff has already been used for simulation, for modeling merger behavior, discovery of new materials, autonomous agents, right? Like, but you could imagine even further out on a 10 to 20 year time scale, things which are currently relatively speculative, but we can easily see in research, right? So like early, vestiges, right? Like early science, right? Digital twins, right? Doubles, right? Imagine a model that knows everything about you, right? Yes.
Two questions. To a young person looking for a career today, what's your advice?
Great time to be a machine learning engineer.
Right. And what do you think about adding politics to this list, like AI government, AI politics?
Yeah, so this is cut off, but at the very end there, if you look at it, there are AI mediated treaties, right? Which is already a thing, by the way, believe it or not. People in the Middle East have a whole lab, right? Where they use AI to evaluate impact of regulations, right? So like, does this conflict with anything that's already on the books, right? And so on. So you could imagine, there are already brain-computer interfaces. The only way to make sense of the neural data, right, is using AI, right? So like, in fact, you could imagine, cross-species communication, right? So like, the model doesn't care that one of you is a dolphin and the other one is a human, right?
Yeah, they're working on it.
Yes, I know. Synthetic telepathy, basically, right? Like you could imagine, evolving these machines, right, instead of building them the way that we build them today. So it's going to be a very interesting next 20 years. That concludes my talk. If you're interested in more AI at Bloomberg, there's this handy QR code. Take a picture, right? Look it up. And I'm happy to take other questions. Yes, Dave. Thank you.
If we're talking about anthropomorphic intelligence, or what we could call sentience, then we need to talk about embodiment, and we can't talk about embodiment without, like we have an enteric nervous system. All of our thinking is centered in a body.
Yes.
We think of inside and outside, and nothing that you described is close to that. And then,
But does it happen?
it gets to be so technically overwhelming, you would basically have to build another human body.
But do you have to, really? Because
Right, and then, I just think, okay, I'll just have another kid.
no, well, planes don't fly the way birds do, right?
No, they don't.
And submarines don't swim the way fishes do, right? So like, then why do we expect that we build machines that think, that have to think the way humans do?
We don't, but I mean, my prediction was always that we were going to have a renewed interest in the humanities precisely because of this problem, because we would want to model ourselves to ourselves.
Right.
And it would be a revival of these things, but that it would also be so technically demanding and
It depends on the fidelity of the
daunting
simulation.
that we
right?
would just be like, we'll build intelligent cockroaches.
It depends on the fidelity of the simulation. This is a long conversation, so I want to give
Yeah.
other people time for
Oh,
questions,
sorry.
right? So, because this we could spend an hour or two, right? Yes.
So I have expertise in a few different areas. Whenever I use ChatGPT, because I have expertise that I've accumulated over a decade, I can evaluate if ChatGPT is right or wrong in certain things. Now you mentioned to an earlier question that younger folks, if they become an AI engineer, it's very helpful for their career. How about folks who want to actually go into, let's say, finance or accounting, areas where earlier we have accumulated expertise over time, but now they're not really, whether or not they're cheating or not learning, but like right now, they don't have the opportunity to learn.
Right. So there was a very interesting Bloomberg news story actually about Norges Bank, which is a sovereign wealth fund of Norway, right, which is a very interesting place, right? So like they manage $1.8 trillion, largest sovereign wealth fund in the world, right? They operate basically as a giant hedge fund, right? Unlike most other sovereign wealth funds in the world, right? And their CEO, Nikolai Tangen, right, had stated on public record that anyone who does not use AI in their job at Norges Bank has no future. They're not going to get promoted, and they're not going to get the job if they apply. So that I think is a partial answer to your question. Right? So this is again, this is one of the most advanced organizations in the world, but the way they go, everyone else will go. Right? So learn to use it. Yes?
What are the areas that you think somewhat privately to yourself or with your closest colleagues that are not the official line of efficient, productive use of AI? But
Yes, by the way, everything I said is my own opinion, not the opinion of Bloomberg.
What are the things that are most privately exciting to you about the potential for AI that if you had unlimited budget, you would be pursuing?
Design of materials, personalized medicine, right? And some of the things having to do with brain-computer interfaces. That's my own biases. Yes.
What was that site you mentioned, the Illustrated something or other?
Illustrated Transformer. Jay Alamar, who is a co-founder of Anthropic. Very smart guy. Yes.
Let's talk a little bit about like multimodal models. I've worked with them, like with image and text. Are people working on like text that started out with all the ticks?
Mm-hmm. Are people working on multimodal models between text and time series? Yes.
And what are their like the names of these types of models?
There are no names because there isn't one that I could point to right now that does anything useful. That's still an open area of research.
Is this like LQMs or is that something else?
Something completely different. Like those architectures look very, very different, right? So like they're more along the lines of neural stochastic differential equations, right? As opposed to pure language models, which gets really deep into the weeds. Right? Yes.
So the thing I'm worried about AI is that one day,
Can you speak up a little bit?
Yes.
Because
So the thing I'm worried about AI is that one day it could destroy like the world we live in. I mean, most of you grew up with Terminator and all those things. But what you said today, on one side there is like deterministic models and stochastic models, and basically those are not able to match our brain. Is that correct? So what would be the missing piece to actually get to this like worst case or best case scenario?
I think there are a lot of missing pieces actually, right? So like I don't think there is a single advance or single missing element or something like that to get to what we would call general cognition or something like that. So I think there are multiple such advances which are still needed, both architectural and methodological in terms of training. And this is not just my opinion, by the way, right? So people who know this field much better than I do, right? Like Jan de Kuhn, for example, or Hinton, or whatever, right? So they are of the same opinion, right? So like that there is still a lot of work to do.
Gary, thank you so much for a great lecture. It was fantastic. Thank you everyone for great questions. If you have more questions, you are invited to join us for a dinner, so you can ask Gary more questions. And I'm glad to see mostly men in the audience. Please bring single girlfriends next time.